In 2012, Ford did something that sounded almost ridiculous. They put a tiny 3-cylinder engine into a family car, 3 cylinders, just 1 liter of displacement, about the same size as a large soda bottle. And then they claimed this little engine could replace larger 4-cylinder engines while delivering impressive performance and better fuel economy. Most people laughed because for more than a century, there was one unwritten rule in the car world: bigger engines make more power, more cylinders mean more speed, more displacement means more torque. It was gospel, the kind of wisdom passed down through generations of automotive engineers. A 3-cylinder engine wasn't supposed to win. It was supposed to power budget cars, microcars, and economy vehicles where performance didn't matter. But what almost nobody knows is that Ford's tiny EcoBoost wasn't just another small engine. It was one of the most ambitious engineering projects the company had ever attempted. And somehow, this little engine ended up embarrassing much bigger engines around the world. Engines with twice the displacement, engines with more cylinders, engines from manufacturers with legendary reputations. So how did Ford pull it off? And why did a 1-liter 3-cylinder engine become one of the most awarded engines of the modern era? The answer is far crazier than most people realize. To understand the EcoBoost secret, you have to go back to the late 2000s. The auto industry was in trouble. Fuel prices were rising. Governments were demanding lower emissions. New regulations in Europe and North America were getting stricter every year. The financial crisis had just devastated the market. Customers were more price-conscious than ever, and they were paying attention to fuel costs in ways they hadn't before. Car companies faced an ugly problem. Customers still wanted acceleration. They still wanted highway power. They still wanted cars that felt responsive and capable. But regulators wanted lower fuel consumption and lower CO2 emissions. European tax structures were beginning to penalize larger engines. Corporate average fuel economy standards in the United States were getting tougher. And China, the world's largest car market, was implementing strict efficiency requirements. For decades, engineers solved performance problems by making engines bigger, more displacement, more cylinders, more everything. Now they had to do the exact opposite. They had to make engines smaller, much smaller. Ford called this idea downsizing. The concept sounded simple. Replace a large engine with a smaller one, then use modern technology to make the smaller engine perform like the bigger unit. Simple in theory, a nightmare in reality. Because small engines have serious disadvantages. They usually make less torque. They struggle at low RPM. They often feel weak when accelerating from a standstill. And when pushed hard, they can become noisy and unpleasant. Nobody wants to hear their family sedan screaming at 5,000 revolutions per minute just to merge onto a highway. Ford's engineers had to solve every one of those problems. And then someone proposed something almost unthinkable: a 3-cylinder engine. Even inside Ford, many people thought it was a bad idea. Product planners worried about customer perception. Marketing teams were concerned about brand image because 3-cylinder engines naturally have balance issues. Think about a typical 4-cylinder engine. The pistons move in pairs, helping cancel out vibrations. When one pair moves up, the other moves down. The forces balance naturally. A 3-cylinder doesn't get that luxury. One piston is always doing something different from the other two. That creates vibrations and shaking forces, primary forces, secondary forces, rocking couples, all the things engineers spend careers trying to eliminate. Historically, 3-cylinder engines often felt rough. They vibrated at idle. They transmitted unpleasant sensations through the steering wheel and pedals. Some sounded like lawn equipment, or motorcycles, or industrial generators. Ford knew if they built another noisy, vibrating economy engine, customers would reject it immediately. But they kept going, because the potential benefits were too significant to ignore. A 3-cylinder engine has fewer parts than a 4-cylinder, fewer pistons, fewer connecting rods, fewer valves, less friction, less weight, all of which translates into better efficiency. And then, the real engineering battle began. The engine they created displaced just 999 cubic centimeters, 1 liter. Technically, they kept it under 1 liter for tax and regulatory purposes in certain markets. Its bore measured 71.9 millimeters. The stroke was 82 millimeters. That long stroke design wasn't an accident. It was absolutely deliberate. Long strokes increase leverage on the crankshaft, helping produce more torque at lower engine speeds. Think of it like a longer wrench handle. More leverage means more twisting force. And torque was absolutely critical, because Ford's engineers knew drivers don't care about displacement numbers. They don't care about bore and stroke measurements. They care about how the car feels. When you press the accelerator at 2,000 revolutions per minute while climbing a hill, does it move? When you need to pass someone on a 2-lane road, does the power arrive? That's what mattered. The first version of the 1.0-liter EcoBoost produced around 123 horsepower and approximately 148 pound-feet of torque. Those numbers may not sound extraordinary today. We've become accustomed to small turbocharged engines, but consider what it was replacing. Many naturally aspirated 1.6-liter engines produced similar horsepower figures and significantly less torque. Some 1.8-liter engines couldn't match the EcoBoost's torque curve, and the torque arrived low in the RPM range. Not at 5,000 revolutions per minute, where it's useless for daily driving. At 1,500 revolutions per minute, right where drivers actually use it. Suddenly, the impossible didn't seem so impossible anymore. But where did all that power come from? One word: turbocharging. Actually, one very clever turbocharger. The EcoBoost used a low-inertia turbocharger capable of spinning at around 248,000 revolutions per minute. That's over 3 times faster than most jet engines. The speeds are almost incomprehensible. At maximum rotation, the turbo's compressor wheel tips were moving faster than the speed of sound. The turbo compressed incoming air, effectively allowing the engine to breathe like a much larger engine. Instead of relying on displacement, Ford relied on pressure, boost pressure to be specific. The turbocharger could generate around 21 psi of boost in higher output versions. That's significant pressure. More air means more fuel can be burned. More fuel means more power. It's basically forcing a small engine to behave like a bigger one, tricking physics in a way. But there was a problem. Turbochargers traditionally suffer from lag. Press the accelerator and nothing. The engine hesitates. Then suddenly the turbo wakes up and power arrives, often violently. Ford couldn't allow that. A family hatchback can't feel unpredictable. It can't hesitate when pulling into traffic. It can't surge unexpectedly when merging. So engineers mounted the turbo incredibly close to the exhaust ports. They designed the exhaust manifold directly into the cylinder head. This was radical thinking. Traditionally, exhaust manifolds are separate cast iron components bolted to the engine. Ford integrated everything into the aluminum cylinder head. This reduced the distance exhaust gases had to travel before reaching the turbocharger. Less distance means less time, less volume to fill, faster pressure buildup. The result? Faster spool up, quicker throttle response, and far less lag. In real-world driving, the difference was remarkable. The little EcoBoost felt responsive from just above idle. It was an elegant solution, but then another problem appeared: heat. And heat is the enemy of every engine, especially tiny turbocharged ones. Remember, this little engine was producing power levels that used to require significantly larger engines. A naturally aspirated engine making similar power might displace 1.8 or even 2.0 liters. The EcoBoost was doing it with just 1 liter. That means every component was working harder, much harder. Temperatures became enormous. Exhaust gas temperatures could exceed 1,000 degrees Celsius. That's hot enough to melt aluminum, hot enough to glow red in darkness. Under those conditions, components can fail, oil breaks down, turbochargers suffer, bearings seize, cylinder heads crack, gaskets fail. Most people don't realize just how hard the EcoBoost worked. At highway speeds, it wasn't casually cruising, it was operating under serious stress. The piston speeds were high, the thermal loads were extreme, the mechanical stresses were intense. Ford needed another trick, so they engineered a split cooling system. Instead of cooling the entire engine uniformly, They could manage temperatures more intelligently. The system used separate circuits for the cylinder head and the engine block. This allowed independent temperature control. The cylinder head warmed quickly after startup, reducing emissions and improving efficiency. Cold engines run rich. They produce more emissions, they waste fuel. By warming the head quickly, Ford reduced the time the engine spent in that inefficient state. Meanwhile, critical components remained protected from excessive temperatures. The turbocharger, the exhaust valves, the piston crowns, and then they went even further. The exhaust manifold's integration into the cylinder head actually allowed coolant to absorb heat directly from the exhaust passages. Think about that for a moment. The exhaust gases, at over 1,000 degrees, were transferring heat to coolant before even leaving the engine. This reduced exhaust temperatures before they even reached the turbocharger. The turbocharger ran cooler, lasted longer, performed better, a remarkably simple idea, and a hugely effective one. But there was still one giant problem left: the vibrations. You can probably guess what happened next. Ford's engineers did something almost nobody expected. They didn't use a traditional balance shaft. Most three-cylinder engines use one because balance shafts help reduce vibrations. They're essentially weighted shafts that spin opposite to the crankshaft. The counterweights cancel out some of the engine's natural vibrations. It works, but balance shafts consume power. They create friction, they add weight, and they reduce efficiency. Ford wanted every ounce of performance and fuel economy. They couldn't afford to waste power spinning a balance shaft, so they engineered around the problem. They intentionally offset the flywheel and front pulley. By carefully designing rotating masses, they canceled enough vibrations without needing a balance shaft. They added counterweights to the crankshaft itself. They tuned the engine mounts. They strategically placed mass in the flywheel. Every rotating component was designed with vibration cancellation in mind. It saved weight, around 3 to 4 kilograms. That might not sound like much, but in engine design, every gram counts. Reduced complexity, fewer parts to manufacture, fewer parts to fail, improved efficiency, less friction means more power reaches the wheels. And it worked. The little three-cylinder became surprisingly smooth, not perfect. No three-cylinder ever is. At idle, you could still tell it was a three-cylinder if you paid attention. But good enough that many drivers had no idea they were driving an engine with one less cylinder. And that was the ultimate test, customer perception. And then the awards started coming. In 2012, the 1.0-liter EcoBoost won International Engine of the Year. Then it won again in 2013, and again in 2014. 3 consecutive victories, an unprecedented achievement. It beat engines from much more expensive cars, engines from Porsche, from BMW, from Ferrari. It defeated larger engines, turbocharged 4s, naturally aspirated 6s. It even outperformed engines from manufacturers famous for engineering excellence. German manufacturers known for precision, Japanese manufacturers known for reliability, Italian manufacturers known for performance. Suddenly the industry paid attention, because Ford had proven something important. Efficiency wasn't just about making cars slower. You could have both performance and economy. The old trade-off didn't have to exist, not anymore. But perhaps the craziest demonstration came when Ford decided to show off. Engineers placed the 1-liter EcoBoost into a Formula Ford race car. Now understand how ridiculous this sounds. A Formula Ford race car traditionally used larger, naturally aspirated engines, usually around 1.6 liters, high revving, screaming to 7,000 or 8,000 revolutions per minute, making power through displacement and engine speed. Ford's tiny turbocharged 3-cylinder entered with around 202 horsepower. That's more than 200 horsepower from just 1 liter, over 200 horsepower per liter. Specific output that would make supercar engineers jealous. Ferrari territory, Porsche territory, from an engine that started life in economy hatchbacks. The race car accelerated from 0 to 60 in under 4 seconds and reached speeds above 150 miles per hour with a 3-cylinder engine, the same basic architecture as what powered rental cars. Suddenly people weren't laughing anymore because they realized something important. This engine wasn't weak, it was simply efficient, and efficiency can be incredibly powerful. When you stop wasting energy, amazing things become possible. But there was another secret: direct injection. Instead of spraying fuel into the intake manifold, the EcoBoost injected fuel directly into the combustion chamber at extremely high pressure, approximately 150 bars. That's over 2,000 pounds per square inch. Massive pressure that allowed more precise control. Fuel could be injected at exactly the right moment, in exactly the right quantity, in multiple pulses if needed. More efficient combustion. Every drop of fuel burned more completely. Less waste, more power, better cooling inside the cylinders. Liquid fuel absorbs heat as it evaporates. Direct injection meant fuel evaporated inside the combustion chamber. That cooled the air-fuel mixture. Cooler mixture means denser mixture. Denser mixture means more power and greater resistance to knocking. Knocking is destructive, uncontrolled combustion. Premature ignition, the enemy of performance engines. Turbocharged engines hate it. High cylinder pressures and temperatures make engines more prone to knocking. Ford's direct injection system helped prevent it, while allowing higher boost pressures. More boost without knocking. More power without destruction. Everything worked together. Turbocharging, direct injection, integrated exhaust design, advanced cooling, long stroke geometry, smart balancing, lightweight construction, variable valve timing. Individually, none of these technologies were revolutionary. Other manufacturers had used turbocharging. Direct injection wasn't new. Variable valve timing had existed for years. Combined, they transformed a tiny engine into something remarkable. The whole became greater than the sum of its parts. Each technology enhanced the others. The turbocharger needed direct injection to prevent knocking. Direct injection benefited from the integrated exhaust design's heat management. The cooling system protected components stressed by turbocharging. It was a complete system, not just a collection of parts. And then something interesting happened across the industry. Everybody started downsizing. Manufacturers everywhere began replacing larger engines with smaller turbocharged ones. BMW introduced 3-cylinder engines. Mercedes followed. Volkswagen doubled down on small turbo engines. Even brands like Volvo eliminated larger engines entirely. The philosophy spread quickly because regulations kept tightening. Fuel economy standards became stricter. Emissions targets became harder to achieve. CO2 regulations in Europe became punishing. Ford had proven the blueprint. They showed the path forward. Smaller didn't automatically mean worse. It could actually mean better. Better efficiency, better response, better packaging. Of course, the story wasn't perfect. Some owners experienced reliability concerns, coolant issues, turbocharger failures, timing belt problems in some markets. Like any highly stressed turbocharged engine, maintenance became critical. Oil quality mattered. The engine needed the right specification, synthetic oil with the correct viscosity. Service intervals mattered. Missing an oil change could be expensive, very expensive. Cooling systems mattered. A small coolant leak could lead to catastrophic overheating. A neglected EcoBoost could develop expensive problems. Head gasket failures, cracked heads, seized turbos. That's the trade-off. When engineers extract big engine performance from a tiny package, components work harder, much harder. They operate closer to their limits. The margin for error shrinks. There's no free lunch in engineering. Everything has a cost. But even critics generally agreed on one thing. The accomplishment itself was extraordinary. Think about it. For decades, conventional wisdom said a family car needed a larger engine, at least 1.6 liters, preferably 1.8 or 2.0 liters. 4 cylinders minimum, 6 if you wanted something nice. Ford challenged that idea, then proved everyone wrong. A 1-liter engine producing the torque of bigger naturally aspirated engines would have sounded impossible in the 1990s. Engineers would have laughed at the suggestion. By the 2010s, it became reality. And today, the EcoBoost's influence can be seen almost everywhere. Tiny turbocharged engines have become normal, standard equipment in mainstream cars. 3-cylinder engines are no longer a joke. They're legitimate alternatives. Hybrid systems often use compact turbocharged engines as partners. The combination of electric motors and small turbo engines is becoming common. The entire industry shifted, the philosophy changed, the assumptions were challenged, all because engineers refused to accept old assumptions, because that's the real secret of the Ford EcoBoost. It wasn't magic. It wasn't some hidden horsepower trick. It wasn't a revolutionary new combustion process. It was intelligent engineering, a long-stroke design for torque, a high-speed turbo for power, direct injection for efficiency, advanced cooling for durability, clever balancing to eliminate unnecessary parts, each decision carefully considered, each compromise thoughtfully managed, each challenge systematically solved. Individually, they were just pieces, components, and concepts. Together, they allowed a tiny three-cylinder engine to punch far above its weight, and maybe that's why this story still matters. Because sometimes, the biggest breakthroughs don't come from making things larger. They come from making them smarter, from questioning assumptions, from refusing to accept that something can't be done. The little 1-liter EcoBoost didn't beat bigger engines by breaking the laws of physics. It beat them by using every bit of physics more effectively, by wasting less energy, by converting more fuel into useful work, by eliminating unnecessary friction and weight. That's the lesson. Not just for automotive engineers, for anyone solving difficult problems. Sometimes the answer isn't more. Sometimes it's better. If you enjoyed this story, let me know in the comments what engine you want to see next. Another EcoBoost, a forgotten V8, or one of the craziest racing engines ever built. And make sure to subscribe so you don't miss the next deep dive into automotive history.